Over the past decades, there are dozens of visual programming languages that have been proposed, along with related systems that allow programming by example or programming by demonstration. Our paper presents a new taxonomy for classifying these systems. We also examine the question of how far these systems can be pushed in terms of expressiveness. Which of these systems can express any program? This is related to the idea of Turing completeness, but we will actually introduce a more stringent criterion that we call GUI completeness. We also propose one particular ultimate goal for the future of this kind of work on visual programming. To motivate our discussion, I'll begin by showing 3 examples of systems. The first is this interface, created by Brett Victor, that allows a person to draw a visualization of some data. In the upper left corner, we have a table of data to visualize, and in the main view, the user draws the kind of visualization that they want of that data. As they draw different shapes and perform manipulations here, a sequence of instructions is generated and shown along the left margin. These instructions specify how to construct the visualization. Here we see the user draw a rectangle, and then dragging and dropping data variables to provide arguments to the instructions. The user then draws a circle, selects a block of instructions, and puts them inside a loop, causing the instructions to iterate over all the data columns. The user continues manipulating the output, building up the visualization. The way the user manipulates the output here can be described as direct manipulation, which can be defined as using physical motions to interactively manipulate visual representations with continuously updated feedback. Not only can the user build up this custom visualization, but Victor demonstrates that the same tool can be used to define bar charts, area charts, pie charts, and various other visualizations. When I first saw this demonstration, I thought it was magic. If programming can be made this easy and direct, maybe programming could be made much more empowering to so many more people. But I also wondered about the limitations of this approach. For example, could this system be used to define more exotic visualizations, like a scatterplot matrix? The answer isn't clear to me. There also seems to be no way to define interactive visualizations. Once the visualization has been programmed, it can be updated by loading a new dataset, but otherwise the output remains static. I wondered if these limitations could ever be overcome, in principle, by a similar visual tool. The second example to consider is Sketch and Sketch. In this system, the programmer can write code, shown on the left, to draw a two-dimensional figure, shown on the right. The programmer can also directly manipulate the figure on the right, which automatically causes the code on the left to update. This can be called bidirectional programming. Here we see the programmer typing code to draw a line, and then 2 lines, and then an array of lines. Next, the user draws a rectangle, causing code to be generated. Updating the code causes the output to also update. Moving the rectangle updates the code, as does resizing the rectangle, or changing colors, or stroke thickness. Next, the user draws some lines. The user wants some of the points to coincide, so the user selects a pair of points and adds a constraint, making those points snap together. The user adds more constraints like this to other pairs of points, and to colors, to stroke thicknesses, and also adds a constraint to the dimensions of the rectangle to force it to remain square. Later in this video clip, the user selects a group of shapes and tells the system to abstract that shape, causing a subroutine in the code to be factored out, making it easier to draw multiple instances of the same group of shapes. Once again, this is some very clever work, and it's exciting to think about how such a paradigm could be applied more widely in programming. However, as with our previous example, the output here is static, and it's not obvious how to extend the system to enable the programming of interactive output. The third example is of Scratch, a popular environment for teaching programming. Scratch uses a metaphor of sprites on a stage. The programmer can draw their own sprites, create costumes for them, and choose backdrops for the stage. The programmer also assembles blocks of instructions to move or modify the sprites on the stage. Each block of instructions is executed in response to some event, such as a key press, a mouse event, or a collision. Scratch supports variables, arrays, loops, and subroutines. Programmers can make games and interactive stories with Scratch. It's possible to make side-scrolling platformer games and even three-dimensional games in Scratch. So consider this question. Are there certain kinds of programs that cannot be implemented in Scratch due to some fundamental limitation of the environment? As we compared these and other systems, we noticed that they often comprise two components, a sequence of instructions shown on the left and some kind of output or data shown on the right, which we decided to call the content. By considering the ways in which a programmer interacts with each of these components and the possible relationships between these two components, we can classify these systems in a taxonomy and better understand the limits of each kind of system. Here are two more examples of programming environments that exhibit the same dichotomy between instructions and content. A web page might be created through direct manipulation in a visual tool like Adobe Dreamweaver. In this example, the web page has some text and a canvas, and then JavaScript code can be added to modify the content of the web page. The Unity game engine also has this dichotomy, where a 2D or 3D scene can be modified through direct manipulation, and also through instructions, as in this example where the code creates the cubes on the right. We can take the 5 examples I just showed you, and for each one we indicate if the content is static or dynamic. The process of programming is always interactive, but once the programming is complete and the content is defined, it appears to the end user either as static or as something that can respond interactively to input, and that's what I mean by dynamic in this column. We can also indicate which systems implement bidirectional updating, so that if the programmer changes either the instructions or the content, the other is automatically kept in sync. Next, which of these systems has a Turing-complete instruction set? The languages here are all essentially imperative programming languages, which means that to be Turing-complete, they need two things: the ability to access an arbitrary amount of memory at runtime, which is achieved if the language supports arrays, and support for conditional jumps, which is achieved if there is support for while loops. These conditions are actually met by most of these examples, including Scratch. But Turing-complete means that, in theory, any algorithm can be implemented. We propose an additional criterion, which we're calling GUI completeness, which is met if the system is Turing complete and also enables the programming of any visual feedback in response to any sequence of input events. If the content cannot respond to input events, then clearly we don't have GUI completeness. But Scratch, it turns out, is GUI complete because there are ways to control a virtual pen or tiny sprites to render vector graphics or pixel graphics. An additional question we might ask is it possible for a system to exhibit all of the desirable properties in this table? Are there programming systems with bidirectional updating that are also GUI complete and by implication Turing complete, and that also allow dynamic content to be defined? I think it is possible to design such systems, and I'll hint at how to do this towards the end of the talk. But next I need to explain some notation. I'm going to use the letters C and I to represent content and instructions. Let's consider the two examples here of Scratch and Sketch and Sketch. How does a programmer interact with the content? In both cases, it's with direct manipulation, so that's shown with the letter D. Next, how does a programmer interact with the instructions? In the case of Scratch, it's with direct manipulation, but in the case of Sketch and Sketch, it's with textual input, so that's shown with the letter T. Now, I'm going to move those two letters to the right end of these formulas to make room in the middle to show the relationship between content and instructions. In both of these systems, when the instructions execute, they have an effect on the content, either by modifying the content or by creating it. That is shown with the left pointing arrows. But in the case of Sketch and Sketch, when the programmer modifies the content, that also causes changes to the instructions. So I'm showing that with a right pointing arrow. Let's combine those two arrows into a double-headed arrow. These are two examples of formulas that summarize these programming systems, and I'll use similar formulas to define the categories in the taxonomy. So here's the taxonomy in the form of a Venn diagram. I'm going to step through each of these categories and show examples. Just to get a high-level feel for the structure of this taxonomy, there's one part on the right for all systems where the programmer can edit instructions, and an overlapping part on the bottom for all systems where the programmer can edit content. The first category is GP, which simply contains systems where the user can edit instructions via textual input or via direct manipulation, and so we'll summarize those two cases with a more general formula where the star indicates any kind of input. A simple example of a system in GP is any traditional text-based programming environment. Here I'm showing a chunk of C# code that prints out square numbers from 1 to 100. The next category is VP, which is a subset of GP. In VP, the programmer uses direct manipulation to modify instructions. Here's a simple example. Actually, this block of instructions does the same thing that I showed in the previous example. It should be clear these two languages are equally expressive, and to make either one Turing complete, all we need is support for arrays and while loops. So why should we bother with a visual language like the one on the right? Well, with a visual programming environment, there's often a menu of instructions that the programmer can choose from. That means the affordances available to the programmer are visible, making it easier to understand what is possible. There's also a metaphor with puzzle pieces, and the shapes of the instructions imply how they fit together, establishing constraints to prevent syntax errors. These are nice features for beginner programmers. Textual programming has other advantages. First, if the programmer is an expert, they can probably input instructions faster by typing them. Second, for a given font size, plain text results in a higher density of information. Third, plain text is easily ported between different software tools. A programmer can easily search for a string and comments and source code using their favorite text editor, regardless of the programming language, and use their favorite diff tool to compare alternative versions of code. It's also easy to programmatically generate text. Some programming environments allow the programmer to switch between these two different views of their code to get the best of both. Another kind of programming that we include in the VP category is flow or data flow languages. I was surprised to learn that these can be Turing complete. In this diagram, there are control connections in white and value connections, which are purple for Boolean, blue for numeric, orange for string, and green for any type. The control flow happens along the nodes connected by the white edges, and these match up with the statements I showed earlier. Below those nodes, we have expressions hanging off as subtrees. The whole diagram is very similar to an abstract syntax tree. There are actually some duplicate nodes shown here for reading the value of j and squaring that value. We can optionally merge those duplicate nodes to get something more compact. It's interesting to notice that with the white control connections, we could have multiple control connections as inputs to one of these triangles, which would mean that multiple statements have the same subsequent statement. But we can only have one control connection coming out of each output triangle because there's only one thread of execution. However, with value connections, it's the opposite. Multiple value connections can be output, but only one can connect to each input. If we compare this sort of flow diagram to other forms of programming, one advantage of having visual connections is that they can reduce the need to explicitly declare and name temporary variables. For example, this product is fed into two other nodes without having to give a name to the product. It's sometimes claimed that flow diagrams suffer from too many connections, too many crisscrossing edges. However, we can reduce the length of edges and the amount of crisscrossing by creating duplicate nodes. For example, this edge is equivalent to this short edge here. It's also been claimed that visual programming languages are not as good for creating abstractions, but in fact, the Bolt environment, which is shown here, allows the programmer to define superunits and macros, and Scratch allows a programmer to define their own subroutine blocks. Next, let's consider tools for editing just content. This includes software tools for editing images, vector graphics, 2D and 3D scenes, animations, and videos. In these tools, there's normally no notion of instructions, just a notion of content that the user can edit, usually through direct manipulation. Within this category of tools, there's a line of research about making use of pen input and sketch-based interaction, from which I've chosen a few examples. Pen input encourages a more informal and creative way of working, and it may make it easier for the user to maintain a state of psychological flow because the user can fluidly switch between inking and command gestures. Pen input is also good for leveraging fine motor skills. The slide here shows one example of a system for sketching simulations. This is an example of a system for sketching animations. and this is a system for sketching visualizations of data. The next category is called PBE, for programming by example. The idea is that the programmer directly manipulates content, which causes instructions to be implied. When those instructions are executed, they themselves have an effect on the content. The slides here show several examples for sketching user interfaces and websites, interactive animations, interactive games with rewrite rules, and data visualizations. The most recent example here is of Lyra 2, which is an exciting system because it allows a programmer to use direct manipulation to define a visualization that is itself interactive to the end user. One advantage of programming in this way is that by directly manipulating the content, there is a smaller representational gap between the target application domain and the programmer's input. Next, we have combinations of the categories I've already shown. The COP category contains systems where there is both content and instructions that can be edited, like these examples which I showed earlier. The content here can be directly manipulated with visual tools, but can also be generated and modified programmatically through instructions. In some programming environments, the content might be referred to as a document, or a scene, or resources, or assets, but the idea is basically the same. In some systems, not only is there both content and instructions, but both of those can be directly manipulated. That's the case with Scratch, and it's also the case with 3D environments like Alice, as well as Modbox. Next, we have systems where editing the content implies automatic changes to the instructions, and vice versa. We're calling these systems bidirectional. This is the case with Brett Victor's system. Although the instructions cannot be freely edited here, the programmer can modify parameters of instructions with drag and drop operations. Sketch and Sketch is another bidirectional system where now the user really can freely edit the instructions, and the instruction set is even Turing complete. And another example we would classify in this category is this GUI designer, which supports bidirectional updating. In the last category, not only is there bidirectional updating, but the user directly manipulates both representations, and we're only aware of one example that falls in this category. Although this work is more than 20 years old, it actually supports 3 representations of the program, and the paper describing the work contains some instructive passages. One way to summarize this taxonomy is to ask, in which categories can we achieve Turing completeness or GUI completeness? It's easy to achieve in any category where the instructions can be edited by the programmer. It's hard to do the same with purely content-based systems because there's probably nothing equivalent to the flexibility of universal computation with such content. The interesting case lies with programming by example, where instructions are indirectly modified through editing of content. How much flexibility can this paradigm achieve? Imagine that the content shown to the user consists of visual representations that are directly manipulated to imply instructions. We can enumerate a few different manipulations of content that could generate fairly generic looking instructions. Selecting an object might make a slider appear, allowing a data member to be modified. Moving an object, maybe to snap it into alignment with another object, is another way that a data member could be modified. Clicking on an object might also pop up a menu of actions, possibly with a submenu of other arguments. It doesn't seem too difficult to add interactive mechanisms to allow for the definition of branches and loops, and to enable different blocks of code to be defined for different input events. There's some other previous work by Brett Victor in his video Stop Drawing Dead Fish that demonstrates related ideas. A programmer might also benefit from being able to nest blocks of instructions inside the nodes of a finite state machine. And related to that, there's a 2014 paper by Stephen Oney and his co-authors, which describes a system called Interstate, which has a very clever and compact way of displaying finite state machines. By combining these ideas, it seems fairly clear how we could build a system that is GUI complete and that can be programmed largely through programming by example, that is to say, largely through interacting with content. Maybe one drawback of such an approach is that showing visual representations for every object we wish to operate on doesn't scale well. It might also be unclear how we could show visual representations of abstract data structures, but it turns out that there's already previous work on that topic, and here are some examples that you might find interesting. One direction we suggest for future work is that programming environments should make it easier for developers to define and leverage bidirectional mappings between portions of source code and the most appropriate visual representations of each portion. Once these mappings are defined, if the programmer makes a change either to the code or to a visual representation, the other should update automatically. We sincerely thank NSERC for funding and offer warm thanks to Brian Hempel for a very insightful email discussion that helped stimulate some of our thinking. Thanks for your attention.